Hello everyone and welcome to Mathematics and Control Engineering tutorials. In this tutorial, we will explain what is a characteristic polynomial of a matrix. In particular, we will first introduce the main motivation behind the characteristic polynomial, then we will state the definition, and then we will solve an example of computing the characteristic polynomials and eigenvalues of this 2 by 2 matrix. So let's start immediately. Okay, so let's start with the main motivation for introducing the characteristic polynomial. The main motivation for defining and introducing characteristic polynomial in mathematics comes from the computation of the eigenvalues and eigenvectors of matrices. For example, let us assume that we have a square matrix A, and for the time being, let's assume that its dimensions are n times n. We write the dimensions like this in mathematics. Now, eigenvalues and eigenvectors of this matrix satisfy this equation. A multiplying the eigenvector W is equal to eigenvalue, that's usually denoted by lambda in mathematics, multiplying W. Okay, so this is the equation that defines the eigenvalues and eigenvectors. To repeat, A multiplying the eigenvalue, actually the eigenvector W, is equal to lambda, and lambda is the eigenvalue multiplying the eigenvector W. The main question is how to find W, that is how to find the eigenvector, and how to find lambda, that is how to find the eigenvalue. We find these two quantities from this equation. Namely, from this equation we have A multiplying W minus lambda multiplying W is equal to 0. Okay, next we have A multiplying W minus lambda multiplying the identity matrix multiplying W should be equal to 0. Now we can group W and we have A minus lambda multiplying I, where I is the identity matrix, multiplying W is equal to 0. And over here I will write that I is the identity matrix. In the case of 2 by 2 matrices, the identity matrix looks like this. It has ones actually on the main diagonals and zeros off diagonals. Okay. So what I did over here, I can simply write, instead of W, I can write I multiplying W, since identity matrix multiplying a vector produces the vector. Okay, so this is the main equation. Now, from this equation, we want to find the eigenvector. And obviously, this equation has a trivial solution. And the trivial solution is W is equal to 0. This is the so-called trivial solution. So what is a trivial solution in mathematics? Trivial solution in mathematics is solution whose all entries are equal to 0. That is, over here, all the entries of W are equal to 0. However, we are not interested in the trivial solution. So I will do it like this. We are interested in non-trivial solutions. So non-trivial solutions. So what are the non-trivial solutions? A non-trivial solution is a solution who has at least a single entry that's not equal to 0. For example, in the case of a 2 by 2 matrix, a non-trivial solution should look like this, for example, or like this, or even like this. the main requirement is that at least a single entry of this vector w is non-zero. So what is the condition for the existence of non-trivial solutions of this equation? Assuming that lambda is known, this is a system of n equations with n unknowns, where the unknowns are the entries of the vector w. And this is a homogeneous system of linear equations. The main condition for the existence of the non-trivial solution is that the determinant of this matrix, A minus lambda multiplying I, is actually equal to 0. Again, this is a necessary and sufficient condition for the existence of non-trivial solutions W inside of this system. This determinant has a special name, and it's called the characteristic polynomial, and we will formally define it in the sequel. However, to summarize everything what's being said so far, if this determinant is equal to 0, then the non-trivial solution W exists. Now, let's define the characteristic polynomial. The characteristic polynomial is formally defined like this. I will define this polynomial as P of lambda, where lambda is the independent variable. And notice that lambda is actually the eigenvalue. And we have that P of lambda is equal to determinant of A minus lambda I. And that's precisely the characteristic polynomial. Namely, if you compute this determinant, you can expand it as powers of lambda. And this is very, very, very important. That is, we will have this determinant will be powers of lambda, and it will be a polynomial. And we will show that in the next example. Now, this is the characteristic polynomial. So what is the characteristic equation? The characteristic equation is defined as determinant of A minus lambda I is equal to 0. And this is the characteristic equation. Now, over here I will erase this minus in order to avoid confusion. And let's state one very important fact. The solutions of the characteristic equation, that is lambdas, that satisfy this equation are actually eigenvalues. This is very important. That is, the eigenvalues are the solution of the characteristic equation, and at the same time the eigenvalues are actually the roots of our characteristic polynomial. That is the roots of this polynomial. And we will do an example in the sequel to illustrate this. To summarize, the characteristic polynomial of any matrix is a polynomial that's computed by taking the determinant of this matrix A minus lambda multiplying the identity matrix. To illustrate the computation of characteristic polynomials and eigenvalues, let's consider this example. Over here, we are given a matrix A, a 2 by 2 matrix, and we want to compute the characteristic polynomial and eigenvalues. So the first step is to form the matrix A minus lambda I. So let's create this matrix. We have A matrix is defined over here. We have 7 minus 4, 5, and minus 2. Over here, lambda is a complex scalar multiplying identity matrix. And the identity matrix is 1, 0, 0, 1. So we have over here, let's do step by step. We will have the matrix A, which will be 7 minus 4, 5, minus 2. And over here, we will have minus complex variable lambda multiplying the identity matrix becomes lambda 0, 0, lambda. That is, the multiplication of a complex variable in a matrix is performed element-wise. And over here we have 7 minus lambda, then we have minus 4, then we have, let's see what we have over here, we have 5, and over here we have minus 2 minus lambda. Let me write it nicely, and let's close this matrix. Next, we need to compute the determinant of this matrix. That is, we need to compute determinant of this matrix in order to create our characteristic polynomial. So let's do that. The determinant of this matrix is obviously 7 minus lambda multiplying minus 2 minus lambda, and over here we have plus 4 multiplying 5. And as the result we will have, let's nicely write it down, we'll have minus 14 over here, then we will have minus 7 lambda, then we will have minus lambda multiplying minus 2, then we will have plus 2 lambda, and we will have plus lambda squared, and plus 20. And finally, our characteristic polynomial becomes a minus lambda I is equal to, let's group terms together, we have lambda squared from this part over here, then we have minus 5 lambda, and over here we will have plus 6. And this is our characteristic polynomial. As you can see, it's a polynomial in lambda. Next, let's compute the eigenvalues. The eigenvalues are computed as zeros of the characteristic polynomial. So we will set over here the characteristic polynomial to 0, and we will compute lambda 1 and lambda 2. Some of you who are advanced students can immediately see the solutions of this quadratic equation. Namely, the solutions can be seen by using a general idea behind the polynomials. However, let's try to find the solution by applying the famous quadratic formula. The quadratic formula gives us 5 plus minus square root of 25 minus 4ac. Over here we'll have minus 4 multiplying 1 multiplying 6, and in the denominator we'll have 2. And this gives us 5 plus minus, this becomes 25 minus 24, and that's 1, square root of 1 becomes 1, 5 plus minus 1 divided by 2. So we have that lambda 1 is 5 plus 1 divided by 2, that's 6 divided by 2, that's 3, and lambda 2 becomes 5 minus 1 divided by 2, that's 4 divided by 2, that's 2. And here it is. So these are the eigenvalues of the matrix A. And that's all for today.